those develop courses go join. I could have teaching.
Nashino. Okay, I think we should start. We'll do that assignment that you have to submit. Yeah.
All right.
It was shared on the group. So we were given a diagram like this. We were given two identical pendulum, each with mass m and length l, and then we have the values of mass and length. Okay, and then it's connected by a spring of stiffness k. We have the spring in between. And then we also have a distance from the spring to the fixed end. So let me just draw the diagram. So the diagram looks like this. We have a pendulum with mass 1, and then in between we have a spring, let's say like this, and then which is mass 2, and then we have the angle to show that it's oscillating. It's gonna be our theta 1, then it's gonna be our theta 2. Okay, and then this one is our k. So this is two identical masses. Two identical pendulum, each with masses, which is M1 and M2. Okay, and then we have the length from here to here, it's L, and from here to here, it's A. And then we are given the length, the values of mass 1, mass 2, and then the value of K, and the value of A, and the value of L. And then we also have a damper between these two masses. We have a damper, okay? We also have a damper here. So we are given that K is equals to what? It's equals to 20 Newton meter. Okay, and then we are given that M1 is equals to M2. M1 equals to M2, which is 10 kg. And then we're also given what? The length, which is 0.5 meter. And then we're also given the value of A, which is 0.1 meter. 0.1 meter. Okay, so as I said, we have a two identical pendulum, each with mass and length, and are connected by what? By a spring. You can see the spring between these two pendulums. Okay, and then we have the damper. So we're not using the value of damper, which means this damper is going to be 0. So our damper is what? It's 0. Okay, and then we are asked to determine the general the equation of motion using Lagrange. And then after that, they also ask us to determine number 1. We're going to determine equation of motion. Okay, and then in number two, we're going to determine the normalized stiffness. Okay, this K with the bar on top, we call it a normalized stiffness. Okay, so first we're going to determine equation of motion. Okay, and then number 2 we're gonna do normalized stiffness, and then number 3, that's where we're going to do what? Eigenvalues, natural frequency, and then we're gonna do the eigenvector, and then we do modal matrix. So here we're going to do eigenvalue, okay, and natural frequency. Number 4, we're gonna do number 4, we're gonna do eigenvector. Okay, and then number 5, that's where we're gonna do what do you call a modal matrix and spectral matrix. Okay, modal matrix, which is P, capital letter P. And then number 6, we're gonna do the spectral matrix, which is this sign, the V that is facing down. Okay, so we are given that diagram. This is the diagram that we're going to focus on, the two identical pendulum. So we're going to use Lagrange method. So remember the Lagrange method, it's T minus U, like this. T minus U, T for kinetic energy, U for potential energy, and then we also have a damper, but our damper is going to be 0, so we won't include it. So if we had the damper, we were going to have the kinetic energy. We're also going to have potential and what? And the damping energy. But now we're going to focus on what? On kinetic and potential, since we don't have damper energy. Okay, so now let's continue and determine the equation of motion. This one, we're going to start by determining the equation of motion. Okay, so to determine the equation of motion, we're going to look kinetic energy. After that, we're going to look for potential. So for kinetic, we're going to focus on the masses. Okay, we have these masses, and then it's oscillating. So we're going to focus on mass 1 and mass 2. So which means our kinetic energy is going to be let me just write on top here. Which is, we're going to use capital letter T for kinetic energy, is going to be half J1 theta dot 1 plus half J2 theta 2, okay, squared, like this. So the J just showing that it's pendulum, it's rotating. So J is equals to what? It's equals to ml squared. Okay, so we're going to have our kinetic energy as half m1 l squared theta dot 1 squared plus half m2 l squared theta dot 2 all squared. Okay, so our kinetic energy is going to look like this. It's going to be half ml squared theta dot squared plus half ml squared theta 2 squared, like this, because we have what? Two masses. We have mass 1 and mass 2 from what? From our diagram. Okay, and then remember it's pendulum, so it's going to be m1l squared theta, the theta, which means we're going to have two generalized coordinates, theta 1 and theta 2. That's why we have what? Theta 1 and theta 2. So we're going to have our generalized coordinates as what? As theta 1 and theta 2. So this is how our kinetic energy is going to look. And then for kinetic energy, remember it's oscillating, it's pendulum, like it's going forth and back and forth. So our potential energy, which is U, so our U is going to be m1 GL into 1 minus cos of theta. We have done this before, but we're doing with one pendulum. Okay, you can just go back to the notes and then see how did we determine the potential energy when we have one pendulum. Still the same thing. Our potential is going to be m1 GL into 1 minus cos theta 1, because now we're focusing on what? On the first pendulum, plus m2 for the second pendulum GL into 1 minus cos theta 2. Okay, and then we have the spring in between. So we're going to have plus 1 over 2k L squared into the difference between the generalized coordinates. It's going to be theta 2 minus theta 1, okay, all squared. So this is our potential energy. It's going to be for the mass 1 and mass 2, and for what? For stiffness, okay. Our damper is 0, so we won't focus on the damper. So now let's continue and look forward for the equation of motion after determining what? After determining the potential energy. Remember, Lagrange formula, it's what? It's T minus U. Or we can write it like this: d over dt into partial derivative of kinetic over dqi. So this partial derivative of qi is our generalized coordinates. I said our generalized coordinates is going to be theta 1 and theta 2, which means we're going to have two equation of motion. Okay, we have a dot here minus partial derivative of t over this, okay, plus du over this, okay, all equals to qi. Remember, the qi is for the force, but here we don't have force, which means it's gonna be 0. If we had the force, we were gonna write the value of force here at the qi, okay, this big letter qi. So now we're gonna let our qi to be theta 1. We're starting by theta 1 and then we're gonna do theta 2, okay. That's our generalized coordinates. So we're gonna let this qi, you're gonna let this qi equals to theta 1. So we're going to focus on theta 1 first. So it's gonna be d over dt into partial derivative of t over d theta 1 dot, okay, minus partial derivative of t over the partial derivative of theta 1, okay, plus partial derivative of u potential over partial derivative of theta 1, okay, like this, all equals to 0, because what? We don't have the force on our first pendulum. We don't have a force on our first pendulum. Okay, moving forward, we're going to derivate t. We're also going to derivate u, okay. So at t, we had half m1 l squared theta 1 dot square plus half m2 l theta 2 dot squared. So but now we're going to focus on theta 1 only. We're going to focus on theta 1 only. So as you can see here, we have theta 1. So which means when we derivate, we're only gonna focus on theta 1 only, since we will let qi to be equals to theta 1. And then when we let qi to be equals to theta 2, we're going to focus on theta 2 only, okay. So when we derivate for theta 1, we're going to focus here. We're going to focus here. So derivative of half m1 l squared theta 1 dot squared, it's what? It's going to be m. We're just going to take this 2 and multiply with half. It's going to be 1. Okay, that's how we derivate. So we're going to left with what? With half, with m1 l squared theta dot squared 1. Okay, we're going to left with something like this when we derivate for theta 1. And then when we derivate for theta 2, we're still going to left with the same thing, but with what? With theta 2. So now let's continue and do the derivative of the first first theta, and then at u, wherever there's theta 1, that's where we're going to focus. So we're going to focus on m1 gl into 1 cos theta 1, and we're also going to focus here at half kl squared theta 2 minus theta 1, because there is theta 1. So now let's move forward. Remember, we have the d over dt into partial derivative of t over theta dot. So we're going to have m1 l squared theta 1 squared. We have the dot here. Okay, we have the dot here. Minus, on our potential, on our kinetic energy, we don't have theta. It's theta dot. So when we don't have a theta, it's gonna be 0 here. Plus, on our u we have m1 on our u we have m1, this m1 gl 1 minus cos of theta 1. So when we derivate this, it's gonna be what? It's gonna be m1 gl sine of theta. And then when we derivate this partial derivative of half kl squared theta 2 minus theta 1, remember we're going to focus on theta 1 only. So here is going to be this 2, the exponent 1 times half. It's going to be k l squared into theta 2 minus theta 1. And then remember what derivative with respect to what? To theta 1. So after writing this, we're going to derivate theta 1. Okay, so negative theta or derivative of negative theta 1 is going to be what? It's going to be a negative 1. A negative 1 multiplied by a negative 1. So on our potential energy, on the partial derivative of u with respect to theta 1, we're going to have m1 gl sine of theta. Derivative of this is going to be m1 gl sine of theta. And then derivative of stiffness is going to be kl squared into theta 2 minus theta 1 multiplied by negative 1, because we're derivative with respect to what? To negative theta 1. Okay, so now let's continue here. We said this one's going to be 0 plus m1 gl sine of theta 1, okay, plus kl squared into theta 2 minus theta 1 multiplied by negative 1. This negative 1 will derivated what? Negative theta 1. So derivative of negative theta 1 is what? Is negative 1. Therefore, we're going to continue or equals to 0. Okay, or equals to 0. So we're going to continue. We're going to derivate this theta dot 1 squared. Actually, here there's no squared. Sorry, guys. It's just theta dot 1. So here we're going to derivate m1 l squared theta dot 1 with respect to time. So it's going to be m1 l squared theta dot. Going to have 2 dots. Okay, 1. Okay, plus m1 gl sine of theta, and then this negative is going to multiply with this one. Then we're going to have negative kl squared theta 2, okay, plus kl squared theta 1. Here I just simplify it. I just say negative 1 multiplied by kl squared is going to be negative kl squared multiplied by theta 2 is this one. Negative 1 multiplied by kl squared is going to be negative kl squared multiplied by negative theta 1. So it's going to be positive kl squared theta 1, or equals to 0. So now we have our first equation. We're going to do the same thing to find what? The second equation. So we're going to let our qi now to be equals to what? To theta 2. So now we're going to derivate with respect to theta 2. Remember, the first equation of motion we derivated with respect to what? To theta 1. So now let's do with respect to theta 2. So we're going to have d over dt into partial derivative of t over partial derivative of theta 2 dot, okay, minus, this is the Lagrange formula, this or equals to qi. But remember, we don't have the force on our second pendulum, so it's going to be 0. Okay, now we're going to derivate with respect to theta 2, and then on the kinetic energy T, we have half m2 l squared theta 2 dot squared. So when we derivate it, we're going to be left with d over dt into m2 L squared theta dot 2 squared, like this, minus 0 because we don't have theta 2 on our kinetic energy, okay, plus on the potential energy we have m2gl into 1 minus cos theta 2. So when we derivate that, we're gonna left with what? With m2gl sine theta 2, okay, and then we also have the what we call the stiffness with theta 2. So when we derivate it, let me just go back. So we derivated this one where we get m2gl sine theta 2, okay, and then when we derivate this, it's gonna be what? This 2 multiplied by half is going to be kl squared theta 2 minus theta 1. But now we're going to focus on what? On theta 2. Derivative of theta 2 is what? Is positive 1. Okay, so therefore we're going to have plus kl squared into theta 2 minus theta 1 multiplied by 1, okay, because we're focusing what? On theta 2. Here it was negative 1 because we focused on theta 1 sharp. So therefore it's going to be equals to 0, okay, and then now we're going to derivate m2l squared. Oh guys, why am I writing squared here? There's no square. Okay, so now we're going to derivate this with respect to time. So therefore we're going to have m2l squared theta dot dot. Okay, we're going to have 2 dots on top of theta. Okay, and then let's move forward. We're going to have m2l squared theta dot dot 2, and then plus m2 gl sine theta 2 plus kl squared into theta 2 minus theta 1, like this, all equals to 0. So this is our second equation. We have the second equation. So the first equation, it was m1l squared theta 1 dot dot plus m1gl sine theta 1 minus kl squared theta 2 minus theta 1. Okay, it was our first equation. This is our second equation. So after getting this, what do you call this equation of motion, we can just assume. Sometimes they will tell you, okay, take theta as they will tell you in the question, they say for small oscillation. When they say for small oscillation, they mean that our sine theta, it can be approximate to what? To theta, okay, and then our cos theta can be approximate to what? To 1. For what? For small oscillation. They will tell you in the question, or you'll just assume, okay. So yeah, if they didn't tell you in the question, you assume, or okay, sine theta will be approximate to theta, and then cos of theta will be approximate to what? To 1, like this. But most of the time in the question, they'll tell you, okay, it's for small oscillation. When they say small oscillation, just know, or okay, they're talking about sine theta will be approximate to theta, and then cos of theta will be approximate to 1 sharp. So now let's write our equation 1 and equation 2 in a matrix form. Okay, so before we write our equation in a matrix form, let's just write this sine of theta in terms of what? In terms of theta. Okay, so our first equation, it was m1 l squared theta dot dot 1, okay, plus m1 GL sine of theta 1, okay, and then minus KL squared into theta 2 minus theta 1, or equals to 0. And now you can see we have the sine theta 1. So we can write our sine theta 1 with what? I mean, in terms of what? In terms of theta. So we're going to have m1 L squared theta 1 dot dot, okay, plus m1 GL theta, okay, for small oscillation, minus we have KL squared into theta 2 minus theta 1, or equals to 0. And then for our second equation, so our second equation is going to be m2 L squared theta 2 dot dot plus m2 GL. So instead of sine theta 2, we're going to write what? Theta. Okay, theta 2. Here's going to be theta 1, and then here's going to be theta 2. Plus KL squared into theta 2 minus theta 1, or equals to 0. So this is our equation of motion. This is our equation of motion. Okay, we have this. So it's m1 L squared theta dot dot 1 plus m1 GL theta 1 minus KL squared into theta 2 minus theta 1. And then our second equation is m2 blah 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 blah. So from getting this equation of motion, we can write this equation of motion in a matrix form. So in our matrix form, we're going to have the mass and the stiffness, m and a k, and then on the side we're going to have the force. Okay, so let's write this equation in a matrix form. So we're going to have on the masses with the theta dot dot, and the stiffness with the theta 1 and theta 2. So now let's write the matrix form. So we're going to have something like this. The first one is going to be theta 1 dot dot, okay, and then this one is going to be theta 2 dot dot, okay, plus here we're going to get the stiffness 1, so it's going to be theta 1, and then we have theta 2, or equals to forces. Our forces were 0, so it's going to be or equals to 0. So now we're going to focus on our what? On our equation of motion, and then we check, or okay, the first row, guys, the first row, that's where we write equation, the first equation of motion. Okay, now let's check our equation of motion. The first one, we have on the theta dot dot, we have m1 L squared, and then here on our first equation we don't have the theta dot dot 2, so it's going to be 0. Okay, and then theta 1 we have mgl. We also have negative, it's going to be positive because negative KL squared minus theta, time is negative theta 1 is going to be a positive KL squared theta 1. Okay, I don't know if you follow him. Let me just rewrite the equation of motion this side. Okay, we have m1 L squared theta 1 dot dot plus m1 GL theta 1. This is going to be negative KL squared theta 2. Here I'm just simplifying. Okay, plus KL squared theta 1, or equals to 0. Okay, and then second equation is m2 L squared theta 2 dot dot plus m2 GL theta 1, and then it's gonna be a positive KL squared theta 2 minus KL squared theta 1 or equals to 0. Okay, now we're going to focus here on the first equation. On our first equation, we have a theta dot dot 1, which is we're going to take the coefficient of theta dot dot 1, which is m1l squared. So we're going to write it here, m1 L squared. Okay, and then here on our first equation we don't have the theta dot dot 2, so it's gonna be 0. Okay, so now we're focusing on the first equation of motion. And then now let's come to the stiffness. On the stiffness side, so we have theta 1. Guys, remember here's theta 1, theta 2, still the same. Even this side is going to be theta 1 dot dot, theta 2 dot dot. So here on our first equation, do we have theta 1? Yes, we do have theta 1. We have it here. So it's going to be m1 gl. m1 gl. And then we also do have theta 1 here. So it's going to be plus kl squared. Plus kl squared. Okay, this space so small. Plus kl squared. Okay, do we have theta 2 in our equation? Yes, we do have theta 2, so is this one. We have theta 2, which is what? Which is negative kl. And then let me just write it with a different color. Then this one's going to be kl squared. Okay, guys, this is negative kl squared. And then now we are done with the first equation of motion. Now let's go to the second equation of motion and then check. Do we have the theta dot dot 1 here? No, we don't have, so it's going to be 0. Okay, do we have the theta dot dot 2 here? Yes, which is what? Which is m2 L squared, like this. Okay, and then we check, do we have a theta 1? Yes, we do have theta 1, which is what? Oh guys, this is 2, not 1. Okay, because we're dealing with the second second generalized coordinates. So do we have the theta 1 here? Yes, which is what? Which is kl squared. So we're gonna write our kl squared here, and then we check, do we have theta 2? Yes, our theta 2 is m2gl plus kl squared. So we have m2gl plus kl squared. Okay, we have that L equals to 0. So our matrix is going to be looking like this, but remember we are given the values. We have the mass, which is 10, we have the length, which is 0.5, we also have the k, which is 20. So now we can substitute into our matrix and then get the value of masses. Remember, this is going to be our mass matrix, and then this one is going to be our stiffness matrix. Okay, so now moving forward, before moving forward, guys, do you have any question? I think I've been talking for the longest time. Do you have any question? Hello, if you don't have, just raise your hand and then I'll continue. Sharp. Thank you. So now we're going to substitute with the values. Our m was 10, and then our L was 0.5, and our K was 20. So 10 multiplied by 0.5 squared is going to give us 2.5. So here it's going to be 2.5, and then here also is going to be 2.5. And then when it comes to this side, it's going to be 10 multiplied by G. G, remember, we know that G is what? Is 9.81. 9.81. So it's going to be 10 multiplied by 9.81 multiplied by 0.5 plus 20 multiplied by what? By 0.5 squared, and then which is going to give us what? 54.05. So let me just write these values in a matrix form, and then we'll be done with the first equation to get the equation of motion. Okay, and then negative k L squared is going to be a negative 20 multiplied by 0.5 squared, which is going to be what? A negative 5. So our matrix form, when we are substituting the values, we're going to have a 2.5, 0, 0, and then 2.5. Okay, guys. like this, and then plus, remember here is going to be theta 1, theta 2 dot dot. Okay, plus the stiffness. Stiffness, we're going to have 54.05, and then here we're going to have the -5, also here we're going to have -5, and then here we're going to have 54.05. So guys, here we just substituted the values that we were given. So here's going to be theta 1 and then theta 2. Okay, all equals to 0. They're all equals to 0. Okay, they're all equals to 0. So this is how we determine the equation of motion. We also write it in a matrix form. Okay, and then the second equation was let me go back. I said the second equation is going to be what? A normalized stiffness. A normalized stiffness. I know we haven't done this, but I'll show you how to determine the normalized stiffness, how to determine the eigenvalue, initial frequency, and the eigenvector. Okay, so I'm just going to show you the formulas. I won't go through the notes and explaining. I'll just show you the formulas, how to determine the normalized stiffness, and all the time you'll be using the same formula to determine the normalized stiffness. You're going to use the same formula to determine the eigenvector and then the initial frequency and eigenvalues. Okay, and the spectral what do you call spectral matrix and modal matrix. Okay, so now let's continue and do this one, the normalized stiffness. After that, we're going to do eigenvalue. Okay, so when we're talking about the normalized stiffness, number 2, this is number 2, which is K bar. Okay, we're looking for K bar. So the formula to determine the normalized stiffness is what? It's m to the power of -12, okay, multiplied by K, multiplied by m to the power of -12. So this formula, we're going to use it to what? To determine the normalized stiffness. To determine normalized stiffness. All the time, we're going to use this formula to determine normalized stiffness. It's m for mass, m to the power of -12 times k is for stiffness, multiplied by m to the power of -12. So this is our mass. This is our K, our stiffness. So we're going to use this matrix to determine what? The normalized stiffness. So what we're going to do, we're going to write the big letter K with the bar, or equals to, and then we write the what we call the matrix of mass, the vector. So it's going to be 2.5, 0, 0, and then we have 2.5 again here, all this to the power of -12. So which means any number that is inside this bracket, we're gonna write the exponent. So it's gonna be 2.5 to the power of -12, 0 to the power of -12, 0 to the power of -12, and then 2.5 to the power of -12. And then K, our K multiplied by our K, which is 54.05, okay, and then here we have -5, even here we have -5, and here we have 54.05, okay, and then we have the last m multiplied by the 2.5, 0, 0, 2.5, all to the power of -1/2. Okay, so what we're going to do here, we're going to do what do you call? We're going to determine this value, the K bar. So we're going to have the 2.5 to the power of -12, and then 0 to the power of -12, and then we get the answers. 2 to the power of 5 to 2.5 to the power of -12, we get the value. 0 to the power of -12, we get this value. So after that, we're gonna multiply and do the determinants. We're gonna do determinants. Remember, this is the matrix, and then we're gonna do the determinants so that we can get the final value of what? Of K. So what we're going to do, just gonna write the answers of 2.5 to the power of -12. So it's gonna be K bar into 2.5 to the power of -12. So it's going to be 2.5 to the power of negative half, which is 0.632. Okay, and then 0 is going to be 0, because then it's going to be what? Let me see. It's unknown. So let's say it's going to be 0 here, 0, and then even here it's going to be 0, and then here it's going to be 0.632 into the same k, into this 54.0 what, okay, and then multiply by the same values of 0.63, and then 0, 0, and then we have 0.63. Okay, so what we're going to do here, we're going to do the determinant. So to determine the determinants, we're going to say we're going to start with these two, with the m to the power of negative half and k. So we're going to say 0.632 multiplied by 54.05. okay, I'm going to say this. Let me just change the color. So we're going to say this multiplied by this, okay, plus 0 multiplied by negative 5, okay, and then after that it's gonna be our first row is gonna be here. This 0.32 is gonna multiply with the 54.05. let's say it's gonna be our value a, okay, and then after determining that, we're going to say this 0 multiplied by negative 5, and then plus 2 plus this 0.0, this 0 multiplied by negative 5, okay, plus 0.632 multiplied by 54. So it's going to be this multiplied by this, and then this multiplied by this. We're going to write it where? Here at a, at b. So it's going to be a, the one that I cross mark, it's going to be 0.632 multiplied by 54.05 plus 0 multiplied by negative 5, and then we get the value, which is a. And then for b, it's going to be 0 multiplied by 5, okay, plus this 0.362 multiplied by 54.05, and then you get the value b. Okay, guys, do you have any question here? So it's this one, the one that I cross, we're gonna multiply this, and then after multiplying, we're gonna add with we're gonna multiply this and this, and then after multiplying, we're gonna say plus 0 multiplied by negative 5, then we're gonna get the value of a. For b, we're gonna say 0 multiplied by negative 5 plus 0.632 plus 54, times 54, 0.5, and then we're gonna get the value b. Okay, let me just write it on the next page. So this is what we have on the other side. We have 0.632 and then 0. We have 0, we have 0.632, and then we have 54.05. We have minus 5. We have minus 5. We have 54.05. And also we also have the other vector, which is 0.6320, and then 0.632. Okay, like this. So what I'm saying, we're gonna start with the first two vectors. We're gonna start with these two first, okay, and then after getting these two to have one vector, and then we're gonna continue and multiply with this one. Okay, so now let's focus on the one that I circled with black. So what I was saying is we're going to have 0.632 multiplied by what? By 54.05. Okay, this is what I'm saying. So it's gonna be our first vector here. So it's gonna be 0.632 multiplied by what? by 54.05, okay, and then plus 0 multiplied by what? By -5. So it's this one and this one for the first corner. So plus 0 into what? -5, like this, okay, and then we get the answer. And then after that, we're going to have what? And after that, we're going to have this number multiplied by this, and this one multiplied by this, and then it's gonna be on our on this corner. So let's say this is our 1, and then this is gonna be our 2. So it's gonna be 0.632 multiplied by -5, okay, and then 0 multiplied by what? By 54.05. Okay, let me just write this way. I don't know. Let me make space. Okay, so here we're going to have 0.632 multiplied by 54.05, okay, plus -5 multiplied by 0, okay, and then on the other side we're going to have the 0.632 multiplied by -5, okay, plus 0 multiplied by what? By 54.05, okay, and then on our second row we're going to have still the same thing but using this part, okay, so it's gonna be 0 multiplied by 54, and then 0.632 multiplied by -5, and okay, and then again we're gonna have 0 multiplied by -5, and then 0.632 multiplied by 54. So what I'm saying is here we're gonna have 0 multiplied by 54.05, okay, plus 0.632 multiplied by -5, 0.632 multiplied by -5, okay, and then for this column, this corner, the last one, it's gonna be 0 multiplied by -5, and then 0.632 multiplied by 54.05. So we're going to have 0 multiplied by -5 plus 0.632 multiplied by 54.05. Guys, do you have any question when it comes to this determinants? And remember, we still have this 0.32. So after getting the answers here, we're going to multiply it. Let's say the answer for this part, we're going to multiply it with 0.63200, and then 0.632, and then after multiplying these two, that's where we get what? The value of what? Of the matrix of a normalized stiffness, okay? We're gonna get the normalized stiffness. Still gonna do the same. So here we're going to have the answer 1, this one, and this one. So we're gonna have one answer. So this answer is gonna multiply with this one, and this one's gonna multiply with this. So and then we're gonna have our normalized stiffness in a what? In a matrix form. We're gonna have answer here, and answer, another answer here, and another one here. Okay, so this is how the what we call the normalized stiffness is gonna look like, okay? And then after getting the normalized stiffness, we can now determine what? The eigenvalue and what? And the natural frequency. We can now determine the eigenvalue and what? And natural frequency. So to determine the eigenvalue, we want to use what? This answer, the normalized stiffness. To determine eigenvalue, you have to use normalized stiffness. Let's say on our normalized stiffness, we get it as what? As 1, 2, 3, 4. Okay, I'm just making an example because I didn't do the calculations here, but you can do the calculation on your own, or I'll just write this quotient on a paper and then scan it. So let's say our normalized stiffness is 1, 2, 3, 4, and now we are looking for what? For eigenvalue and natural frequency. For eigenvalue and natural frequency. So guys, every time you have to get this normalized stiffness right, right, because you're going to use it to determine the natural frequency and normalized stiffness. Like you have to get it right. You don't have to make any mistake, because we're going to use the same answer that you get here to determine other answers. To determine the next questions. Okay. So now let's say they want us to determine eigenvalue and natural frequency. Okay, natural frequency. So remember our normalized stiffness. I'm just making an example. We have 1, 2, 3, 4. Let's say our normalized stiffness, we find it like this as 1, 2, 3, 4. Okay, so to determine these two, the eigenvalue and the natural frequency, we're gonna use the determinants. We're gonna use determinant k minus lambda I, okay, or equals to 0. Okay, and then I is equals to 1, 0, 0, 1, always, okay, always I is gonna be equals to 1, 0, 0, 1, like this. So to determine the eigenvalue, remember this sign is for what? It's for eigenvalue. Okay, so now we're looking for what? For eigenvalue. What we're going to do, we're going to determine this. So we're going to have the determinant of what? Of k. Okay, but remember this one is what? It's the normalized stiffness. So now we just want what? The value of k. Remember, we do have the value of k. We did determine it. So the value of k is going to be what? It's going to be 54.05, negative 5, negative 5, and 54.05. Okay. No, guys. It's stiffness, not... It's normalized stiffness, not stiffness. Let's see. Here it's normalized stiffness, not just stiffness. So it's the normalized stiffness here. So remember, I said here these values, we just wrote them because we didn't calculate on our previous question when we determined the normalized stiffness. Let's say our normalized stiffness is 1, 2, 3, 4, and then what we're going to do here, we're just gonna write this 1, 2, 3, 4 here, minus, we have the lambda, minus lambda into, I it's 1, 0, 1, 0. 0, 1, like this, okay, or equals to 0. And now we are looking for what? For the lambda. So how are we going to look for the lambda? So remember, here we're going to say this negative lambda multiplied by y, negative lambda multiplied by 0, so, and then that's where we're going to determine what? Lambda. So we have the determinant into 1, 2, 3, 4. Remember, here we're gonna have the exact values that we get it on normalized stiffness, and then negative lambda multiplied by 1 is gonna be, let's say here it's gonna be negative, into lambda multiplied by 1 is lambda. It's gonna be lambda, and then lambda multiplied by 0 is 0, and then 0 multiplied by lambda is 0, and then 1 multiplied by lambda is lambda, like this. Okay, and then after that it's gonna be 1 minus lambda. So we're going to have 1 minus lambda, okay, and then 2 minus 0. 2 minus 0 is gonna be 2. We have 2, and then 3 minus 0 is gonna be 3. 4 minus lambda is gonna be 4 minus lambda, okay, or equals to 0. And now after here we can determine the lambda using what? Determinants. So it's gonna be negative 1 minus lambda multiplied by 4 minus lambda. So it's gonna be going like this, okay, and like this. So it's gonna be 1 minus lambda multiplied by 4 minus lambda minus 2 multiplied by 3, or equals to 0. Okay, so that's how we determine what? The eigenvalue. Eigenvalue is the lambda. Okay, so we're going to have 1 minus lambda multiplied by 4 minus lambda minus minus 3 multiplied by 2 or equals to 0. Now we're looking what? We're looking for lambda. So it's going to be 1 multiplied by 4, which is 4. 1 multiplied by negative lambda is going to be negative lambda. Negative lambda multiplied by 4 is going to be negative 4 lambda. And then negative lambda multiplied by negative lambda is going to be a positive lambda squared plus 6 or equals to 0. Guys, remember these values of k we were just assuming. It's not the correct one. So now we can write this equation of motion, this equation in a standard form. So we're going to have the lambda squared minus lambda minus 4 lambda is going to be minus 5 lambda. Okay, 4 plus 6 is going to be 10 or equals to 0. And then now you can use the quadratic formula and get the value of lambda. Okay, let's say our lambda is going to be 0.1. I'm just making an example, guys, here. And then let's say it's going to be our first lambda. And then our lambda 2 is going to be 3. Okay, I'm just making an example here. Okay, and then after here, we're not done, but this, we call them what? Eigenvalues. When they say determine eigenvalues, you use determinants. Okay, so this one, we call them what? Eigenvalues. Okay, and then now when they say determine natural frequency, we all know that natural frequency is equals to lambda is equals to square of natural frequency. So to determine this, is gonna be natural frequency is equals to square root of, is it? Yes, square root of lambda, like this. So which means our natural frequency 1. What am I doing, really? Yeah. So our natural frequency 1 is going to be the square root of eigenvalue 1, and then our natural frequency 2 is going to be the natural square root of eigenvalue 2. And then you get the value of what? Of natural frequency. This W, we call it natural frequency. That's how we get what? Natural frequency. Okay, so natural frequency is just a square root of what? Of lambda. You start by getting the eigenvalue, and then after getting the eigenvalue, that's where you can get what? The natural frequency. Natural frequency is a square root of eigenvalue. Okay, guys, and then I said after determining the eigenvalue, we can determine the eigenvector. Okay, we can determine the eigenvector. What time is it? Is it 8 o'clock? And then to determine eigenvector, we have the formula for eigenvector. Okay, so the formula of eigenvector, it's the normalized stiffness. That's why I said, guys, don't make mistake when you are calculating the normalized stiffness, because we use it to our next questions. So the formula for eigenvector is the normalized stiffness minus lambda, okay, multiplied by I. Remember, I, it's 1, 0, 0, 1, okay, and then multiplied by V. V for what? For vector, or equals to 0. Okay, and remember, we have lambda 1, we will also have lambda 2, which means we're going to have 2 vectors. Okay, we're going to have 2 vectors. So to determine this vector, we're going to use this formula. So we're going to have the normalized stiffness minus lambda 1, okay, multiplied by I into V1. V1 is for vector 1, okay, or equals to what? It's equals to 0. So this V1, we can write it in a vector form. We can write it in a vector form like this. So, sorry. So after here, we can write our V1 as 1 over square root of 1 squared plus V21, okay, 1 of V21, like this. So we can write our vector. This is the formula of v1. So what we're going to do here, we're going to look for v21, so that we can get what? v1. So how are we going to get this v21? We're going to write our formula in a matrix form like this. We're going to substitute our matrix form of normalized stiffness, which was 1, 2, 3, 4, like this, okay? And then minus our value of lambda 1. Let's say our value of lambda 1, that side we just estimated as 0.1, okay? Multiply by 1, 0, 0, 1, like this. And then v1, we're going to write it like this, 1, and v2, 1, okay? All equals to 0, all equals to 0. So remember, we're going to look for what? For v21. So to look for v21, what we're going to do, we're going to add, we're going to multiply this 0.1 with this one. So it's going to be 0.1 multiplied by 1 is going to be 0.1, and then 0, 0, and 0.1. So after that, it's going to be 1 minus 0.1, 2 minus 0, 3 minus 0. So we're going to have 1 minus 0.1, and then 2 minus 0, and then 3 minus 0, and then 4 minus 0.1. okay, I just multiply 0.1 with 1 and 0. Okay, so after here we're going to have 1 and v21, all equals to what? Equals to 0, like this. So 1 minus 0.1, you get the answer, and then here it's going to be 2, 3, and then 4 minus 0.1, you get the answer. And remember, on top here, still the same, is 1, v21, okay? And then now let's move forward and calculate what? v21. So to get v21, we just have to simplify this. 1 minus 0.1, 2 minus 0, 3 minus this, so let's say we're going to have 0.9, we have 2, we have 3, we have 3.9, okay, like this. And then we have 1, v21, all equals to 0, and here still the same. So now we can have the equation from this matrix. So remember, this 0.1 it goes with 1, this 2 it goes with v21. So we're gonna have 0.1 multiplied by 1 plus, because it's positive, if it was negative, we're gonna say negative, plus 2 v21, all equals to 0, okay, like this. And then now we can solve for what? For v21. So v21 is going to be a negative 0.9 divided by 2, and then you get the answer, v21. Okay, you get the answer, and then after getting the answer, that's where you get what? Your v1. Remember, v1 is equals to 1 over square root of 1 squared plus v21, and then we have it's a matrix, it's a vector, 1, v21. So now we have the value of v21. Let's say our v21 is a, it's answer, okay? You're gonna get the value of a, and then now we're gonna substitute here and then get the vector v1, okay? Get v1. Let's say here it's gonna be 1 over 2 into 1, and then v21, let's say it's a, okay, like this. And then our v1 is gonna be like this, 1 over 2 a into 1 a into 1 and a. Okay, so this is how we determine v1. Same thing to v2, same thing to v2, but on v2 we're going to use second lambda. We're going to use what? The second lambda. Remember, here we started by using what? Lambda 1. So which means when we're going to determine v2 here is going to be what? It's going to be lambda 2, and then here is going to be what? v2, and then we're still going to have the formula. So but on the formula we can now use different v numbers. So we can use v11, any v, and then the sub what do you call this sub number, you can use v11. So we're gonna have 1 over square root of 1 squared plus v11 into 1 v11, and then you follow the steps that we did when we're calculating what? v1. So that's how we determine what we call we determine vector, eigenvector. We use the formulas. We're going to use V1 and V2. After that, I say we're also going to determine the modal matrix and the spectral matrix. So the formula to determine this modal matrix and spectral matrix. So let's say our V1, we get it as 1 over 2 1a, and then let's say our V2, we get it as 1 over 2 a1, a and 1, like this. Let's say V1 and our V2, we find them like this. And then to determine the modal matrix, when they say determine the modal matrix, we have P. P is for modal matrix, okay? It's equals to into V1, V2. So what you're going to do here, you're just going to write your matrix. So it's going to be 1 over 2, and then we're also going to have 1 over 2a. We just multiply this 1 over 2 with 1 over 2 with a. And then V2 is going to be 1 over 2a, and then 1 over 2. So this is how we determine what? The modal matrix. You use the eigenvectors, okay, to determine what? The modal matrix. And then to determine the spectral matrix, we have the formula, but that formula, it was gonna lead us to, I'll show you, it's gonna lead us to what? So what do you call the spectral matrix? So spectral matrix, we have this formula, we write it like this: P to the power of T, normalized stiffness, multiplied by P. So guys, this whole thing, it will give us, it will end up to what? To lambda 1, 0, and 0, lambda 2. So what you have to do, you just have to write this equation, and then at the end you substitute this P to the power of T. This P to the power of T is just sharpen the values of P. Remember, on P, where's P? This is P. Remember, on P we have half a, and we also have half a, half. You just swap these two values. The other one is going to be negative, the other one is going to be positive. Just swap them to get what? The P to the power of T. Okay, so the P to the power of T, let's say this one was negative, just going to change this negative to this one. It's just the inverse. Okay, and then after substituting everything, after, not this one, okay, after substituting everything, the P to the power of T and the normalized stiffness and the P, your answer is going to give you the lambda 1 and lambda 2. So in summary, we can say the spectral matrix is equal to what? It's equal to the lambda 1, 0, 0, lambda 2. So every time when you substitute your values, the P to the power of T, the K, normalized stiffness, and the P, you're going to get the answers as lambda 1 and lambda 2. So you can just write, okay, your spectral matrix is equal to what? It's equal to lambda 1, 0, and then 0, lambda 2. So this is what we do when we have that kind of equation. They're just gonna ask you to determine the equation of motion. After determining the equation of motion, and then you have to write in the matrix form, and then they say, okay, determine the normalized stiffness. We have the formula for normalized stiffness. So the first one, you determine equation of motion and then write it in a matrix form. And then number 2, you're going to determine the normalized stiffness, which is m to the power of negative half k m to the power of negative half. And then number 2, you're going to determine the eigenvalue, where you're going to use the determinant k minus lambda I, and remember I equals to 1, 0, 0, 1. So I equals to that. Okay, and then after here you're gonna determine what we call eigenvalue. After eigenvalue, you're gonna determine the natural frequency, which is square root of the eigenvalue. And then number 4, we're gonna determine what the eigenvector, where we have the formula for eigenvector. I wrote it there at the back. And then after that, you're gonna determine what this is vector. And then here we're gonna determine P, which is V1 and V2. Okay, and then this, which is lambda 1, 0, 0, lambda 2. So this is what you have to do when you have that kind of question. I think we're gonna stop here, guys. Thank you for joining the class. If you have a question, just ask or just send me a message, and then I will help you. Sharp. Good night.